So this is a table that summarizes the formalisms in statistical mechanics. There are three main kinds: Maxwell-Boltzmann, Bose-Einstein, and Fermi-Dirac. And if you go down the list, you can see that the different kinds of particles that exist. So for example, the Maxwell-Boltzmann statistics gives the classical definition. Bose-Einstein statistics gives the quantum, and Fermi-Dirac give also the quantum statistics. The types of particles in them are, for the Maxwell-Boltzmann, is distinguishable. The number of particles per state are unlimited. The number of particles in a system are constant. Total energy is also constant. They are spin zero. And types of example for Maxwell-Boltzmann are gas molecules, usually at high T and low P. Bose-Einstein statistics are basically for bosons. Remember, they are for indistinguishable quantum particles with spin zero or integral spin. Fermi-Dirac are for fermions. They are half integral spins. They are limited to one particle per state. The details are also given in the book. I will highly recommend that you guys read those. Now, another thing that I found very, very useful when I was trying to think about how to make this into a collection so that we can understand it is this flow diagram. So if you remember the other flow diagram that I showed you at the beginning of this class was this one. And we talked about a system, a microstate, an ensemble, a distribution, a degeneracy, and a microstate. And then we went towards the wings of this rib cage. So now I want to show you how these two wings sort of come together. And in that case, what I want you to see is I'm going to go towards the right side of this rim and sort of make you come back to the entire universe. So going back to the other flow chart that I want to show you now is this one. So at the top, I still have my fundamental system at the top. Then I have my microstate. Then I have my macro state, which is now divided into two parts, the classical statistics and the quantum statistics. Now, there are two distinguishable things in classical statistics. One is for distinguishable particles and one is for indistinguishable particles. When we're talking about distinguishable particles, I'm basically talking about solids. And we talked about it in a sense that solids, by the virtue of their placements, can be told where those locations are, and those are called those statistics are called Boltzmann statistics. Now, for indistinguishable particles that include gases and liquids, the statistics that we follow are called Maxwell-Boltzmann statistics, and we talked about the fact that those are in that case, there is no limit on the occupation number in this particular case. Now, moving on to the quantum part, the two that we discussed were Bose-Einstein and Fermi-Dirac, who are separated on the basis of the occupation number, whether they can be one particle per quantum state or whether they could be number of particles per quantum state. That distinguishes these two statistics into Bose-Einstein or Fermi-Dirac. Fermi-Dirac, the occupation number is one per state, whereas in the Bose-Einstein, there is no limit on the number of particles themselves. When particles follow the Bose-Einstein statistics, they're called bosons. When they follow Pauli-Dirac exclusion principle, they are called fermions, and they follow the Fermi-Dirac statistics. Further, those can also be defined in terms of baryons and leptons and mesons if you're talking about particle physics. And those collectively will now be called hadrons and leptons combined together will give you matter particles and the entire universe. So you can approach it from many different ways, and this flow chart sort of helps you navigate from quantum to statistics to particle, and in fact, the entirety of our universe. So I really like these two flowcharts, and they give you the entire universe in a nutshell. Now, the last thing that's left is for me to talk about the left side of this picture. The left side of this picture actually defines my entire system in the types of system. So I can now talk about the things that I was talking about in chapter 3, which is closed, isolated versus open systems. And how does statistical mechanics define those kinds of situations? So let's talk about those now.